Hello everyone and welcome back. My name is William. Today I want to continue our journey into the world of dynamic programming by looking at a very unique problem. In this video, we are going to look at the solution to the narrow art gallery problem, a problem that featured in the 2014 ICPC North American qualifier. When I was just starting to learn about dynamic programming, I ran into this problem and was totally unable to make any progress of any kind. That is until I attempted it several years later. I hope that my solution will enlighten you and enable you to tackle more difficult problems you're facing in your own life. Let's begin by defining the problem. A long art gallery has two n rooms. The gallery is laid out as n rows of two rooms side by side as shown in the figure on the right. Doors in the gallery connect all adjacent rooms, allowing customers to navigate the gallery. However, there's a complication. The gallery manager must close off K rooms because of staffing cuts. Furthermore, visitors of the gallery must be able to enter using at least one of the two rooms at one end of the gallery, proceed through the gallery, and exit from at least one of the two other rooms at the other end. What this means is that you can think of the bottom two rows of the gallery as the entrance and the top two rooms of the gallery as the exit. Now here's where it gets interesting. The manager has also determined how much value each room has to the general public. And now she wants to close off those K rooms that leave the most value available to the public without blocking a passage through the gallery. And that's the key information there, without blocking a passage through the gallery. So in summary, the grid on the right represents a gallery of rooms full of art. Guests enter from the bottom two rooms and navigate the gallery, moving upwards. Each room has a score representing the aesthetic value of the room, and we want to maximize the overall value of the gallery by closing K rooms, which still allows a passage through the gallery. Let's have a look at an example. Suppose we're dealing with the gallery on the right and the manager needs to close K equals 5 rooms due to staffing cuts. One optimal solution is to close all the rooms highlighted in purple. This still allows visitors to navigate the gallery from bottom to top while maximizing the total cost of all open rooms, which for this gallery is 102. Notice that we can focus on minimizing the cost of closing K rooms to maximize the overall cost of open rooms by simply subtracting the cost of all the rooms by the cost of closed rooms. So from now on, we'll just be focusing on minimizing the cost of closing K rooms for simplicity. However, before we get too far into this problem, I think it would be great if you attempted the problem. I've said it before and I'll say it again. The best way to learn dynamic programming is with practice. Follow the link at the bottom of this slide to get access to the narrow art gallery problem. I will also place a link in the description. I also have a few hints for you guys. My first hint is it ever possible to close off two horizontally adjacent rooms in the gallery? What about diagonally adjacent rooms? And my second hint is that K, the number of rooms to close, is part of the DP state, and so is N, the number of rows in the gallery. But there's also another parameter we need to keep track of, but I will not say what. Alright, before we get into the solution, let's try and better understand the narrow art gallery problem itself. In the problem description, we're told that K is the number of rooms the manager needs to close. Let's suppose we're given a gallery on the right and then the number of rooms to close is K equals 2. You may be tempted to close off rooms with values 0 and 1 to minimize the overall cost. However, this would be a mistake since we must ensure that clients can navigate through the gallery. The same applies for two adjacent diagonal rooms. So instead of closing the room with a value of 1, we should instead close the room with a value of 2, which gives us the optimal solution of 2 for this gallery and the number of rooms to close. Now, as an exercise, what is the optimal solution for this gallery when k equals 3? Feel free to pause the video. I'll give you a moment. One optimal solution is to close the rooms valued 2, 0, and 4 as shown on this slide, but you could have also closed the rooms valued at 2, 1, and 3 for the same answer. Typically, there are two main ways to approach dynamic programming problems, which is either top-down or bottom-up. In today's approach, I'm going to focus on the top-down approach because it feels more intuitive to me, even though the bottom-up approach should yield the same recurrence relation. When approaching a problem top-down, we're going to try and see if we can make the problem simpler for ourselves. And a gallery can be made simpler in the following ways. The first is by making the gallery smaller. Instead of considering a gallery with r rows, consider a gallery with r-1 rows. And the second way to make the gallery simpler is by reducing the number of rooms that need closing. For example, instead of requiring k rooms to be closed, require only k-1 rooms to be closed. The hope is that by finding solutions to simpler galleries that we can later either combine or break down galleries into finding an optimal solution. Let's begin by enumerating all possible galleries filled from top to bottom. The shape of a gallery is represented by the squares highlighted in brown. The gallery we're trying to find the optimal solution for is the leftmost gallery, and the other galleries are simpler galleries for which we're choosing to include fewer rows and columns. One thing that's important to note as we start laying out the shapes of possible galleries is that we're specifically choosing galleries which are continuous and can be constructed from bottom to top without any gaps. This allows us to incrementally build solutions by blocking off rooms in the gallery one at a time. If we assume that k equals 1, meaning we need to close off one room, then we can easily see that the best value for each smaller gallery is. In this slide, I highlighted the closed rooms for each state in purple and wrote the best value for each state below it. We can also take it one step further and consider all galleries where we need to close k equals 2 rooms. Here you can see the optimal solution where we require 2 rooms to be closed. First, note that the bottom rightmost galleries have an optimal solution of positive infinity. That is because there is no solution which involves closing 2 rooms for those galleries, either because there are not enough rooms or closing 2 doors would block a passage through these smaller galleries, which we do not allow. And similarly for k equals 3, and so on. I would like to remind everyone right now that what we are ultimately after is the optimal solution for the whole gallery, and not what individual rooms we're actually closing. Even though in the previous slide I displayed some purple squares to highlight which rooms gave the optimal solution, there may be more than one possible way to achieve the best value for a gallery. We also observed earlier that the manager cannot close 2 horizontally adjacent rooms. This means that for states which include a row with both left and right columns, that only the left or the right room may be closed. This is interesting because more generally it means that states which consider both the left and the right column end up deriving their value from states with either only the left or the right column selected. For example, in the full row state on the left, we cannot close both the rooms 5 and 9 because this would block a passage through the gallery. So what ends up happening is that the best value from the left or the right column state gets selected. This leads to an interesting conclusion that the full row state is actually not a canonical state, but rather a derivative state. This means that we don't explicitly need to track the value of the full row state because we can simply dynamically calculate it as the minimum of the left state and the right state in the same row. I'll let that soak in for a while. Returning back to our gallery of galleries right here, you can see that the value of the full row state is actually just the minimum of the left and the right column states as illustrated. So rather than continuing to track the full row state, I'm simply going to remove it from the picture And these are the gallery states we need to work with. Taking a closer look, you can see that each gallery is uniquely represented by a triplet of 3 values. K, the number of rooms to close, R, the number of rows in the gallery, and C, either the left or the right column. As a side note, C was the missing parameter given in the second hint. Let's take a moment to better understand how we're representing a state. Here we have 3 different galleries. Assume that for each of these galleries that k equals 1. Knowing that, what is the state triplet for each of these galleries? To determine the state, identify the upper left or right cell. This gives you the row column position of the state. So the left state is represented by the triplet k equals 1, r equals 3, and c equals 0, while the middle state is represented by the triplet k equals 1, r equals 2, and c equals 1. Now that we understand how each state is represented, we can list out the triplet values for all the states. Notice that our column values for C are always either 0 or 1, since galleries can only have a width of 2. So to simplify things, I'm going to replace the values of 0 and 1 with the constants left and right, respectively. So the big question you've probably been wondering is, how do we transition between states? Because that's not obvious at all. Since we are approaching this problem from a top-down manner, I'm going to walk you through how to decompose a state into smaller states to form a recurrence. For this example, we are trying to find the best value we can get by closing k rooms in the region highlighted in brown on the left. The room that we're trying to determine whether to leave open or close is cell 6 in the upper left column. The first transition is when we choose to close room 6. In this situation, we add the value of room 6 to the solution and recursively call the function f to determine the best value for the region which does not include room 6 below it, which is the smaller region in brown in the image. Notice that when we choose to close room 6, that in the recurrence, we no longer have k rooms to close. Instead, we have k minus 1 rooms left to close because we just closed the room. I think it's also important to note that we are specifically choosing the best value from a left gallery since room 6 is on the left side. If we chose the best value from a gallery on the right, there's a chance that we could end up blocking the passage through the gallery by having 2 diagonal rooms closed at the same time. However, there's more. We also need to consider the best value from the state which does not include cell 6. This is because perhaps closing 6 doesn't belong in the final solution. For this situation, simply consider the region in brown which doesn't include cell 6, but still has k rooms that we need to close. Essentially, we're delegating the problem to be solved in a smaller gallery. But remember that the full row state can be calculated as the minimum of the left and the right states as shown. So if we simplify the diagram by removing the intermediate state, we get that the left gallery is derived as a recurrence from 3 smaller galleries. I also want to take a moment to look at the case where we have a right column state and how to handle that case. Well, as you can see, by symmetry, we have the same recurrence, but everything is flipped for the right side, and it's as easy as that. Alright, let's take a look at some pseudocode. I'm sure some of you are eager to know how this is coded. As with most problems, let me walk you through some of the variables we have at our disposal. The first 2 variables are the constants left and right, which simply represent the values 0 and 1 for the left and the right gallery columns, respectively. Next is inf, a large infinity value. A value of 1 million is quite sufficient for the bounds specified in this problem. Following this is n, the number of rows in the gallery. We are told that there will be a minimum of 3 rows in the gallery and a maximum of 200. Next up is k, the number of rooms the manager needs to close in the gallery. After that is the gallery matrix, which is a 2D integer matrix of size n by 2 containing the value of each room in the gallery. I arranged the values in the gallery so that the bottom left gallery value is accessed at row 0 in the left column, and the top right room value at row n-1 in the right column. This is done so that you can imagine galleries like I animated in the previous slides, where customers enter from the bottom and exit through the top of the gallery. I don't think you'll get a different final answer if you don't reverse the gallery values. It'll just be as though galleries are being constructed from top to bottom rather than bottom to top. You'll also get different partial state values, but the final solution should be the same. The last value is the DP table, which is a 3D integer matrix of size k plus 1 by n by 2, initially filled with null values. The value of DP at KRC represents the partial state with K rooms closed, R rooms processed, and column C selected in the current row, where C is the constant either left or right. So to kick things off, we have a simple solve method. We begin by finding the sum of all the rooms in the gallery by adding the value of all the rooms together. And then we return the total value of all the rooms we can keep open while closing K rooms due to staffing cuts. So the real interesting stuff is what's happening inside the function f, which finds the minimum value we can achieve by closing K rooms. As input to the function f, I provide k, the number of rooms we need to close, and n-1, which is the row index for the height of the gallery. Alright, so here we are inside the function f. Feel free to pause the video and try to understand the function before I walk you through it. Inside this function, we're taking the min of the top left and the top right gallery states. If we illustrate this, the function f of kr left finds the optimal way to close K rooms while exiting in the top left room, and f of kr right finds the optimal way to close K rooms without blocking a passage through the gallery while exiting using the top right room. So together, these find the optimal solution for the whole gallery when we take the minimum of the two. Alright, let's dive into the real guts of the recursive function. First, notice that this function is also called f, but has 3 parameters instead of 2. Our first base case is when we have finished closing K rooms. In that case, we can just return 0 to indicate that we are done counting. The other base case is if we ever encounter a negative row value. Then we know that we've gone too far and that the gallery is too small, so return infinity to make sure we don't include this state. Next, we check if we've already calculated the solution to this partial state, and if we have, then return the solution. It might not be evident, but partial states in this problem overlap quite a bit, especially because the gallery is narrow. Without this line, the runtime would be super slow. After that, extract the value of the room we are considering closing from the gallery matrix at the current row column position. This next part is where all the action is happening. Depending on what the value of C is, we are either trying to calculate the region displayed on the left or the region displayed on the right. The recurrence for this function is broken down to 3 parts, and we are going to take the minimum value returned by the recursive calls and store it in our DP table. The first recursive call is the one that handles actually closing the current room. If we were to visualize it, it may look something like this, where f of k-1, r-1, c represents the region in brown, and the blue cell is the room we are closing. Notice that the room diagonal to the room being closed is left open. This is so that a passage through the gallery doesn't get blocked. After that, the following 2 recursive calls return the best value, which close K rooms but doesn't include the current room. In the first call, we consider a smaller gallery in the same column but with fewer rows. In the diagram on the top, the red outline is the state we are trying to find the solution for, and the brown cells represent the smaller region we're considering, which doesn't include room 5. In the following line, we do the same thing, but we consider the opposing column. So if the value of C is left, then we would consider the right column and vice versa. However, a simplification we can make is to replace C and C XOR 1 with left and right, since both sides are called anyways no matter what the value of C is. However, if you prefer, or if it's easier to understand, you can simply call f of k r minus 1, which is the same as getting the minimum of f of k r minus 1 left and f of k r minus 1 right. Awesome, and that's all I have for the narrow R-gallery problem. I hope you learned something new, and I'll catch you next time. Please remember to like this video and subscribe for more mathematics and computer science content. Thank you.